So next speaker is Oliver. He's doing his PhD at KTH right now, and he's going to talk about something that is like an attempt at getting general superintelligence, general artificial intelligence. I would say. I'm not sure. He will explain it better. And I think that the slides for the presentation will hopefully be up in the Facebook event later, just so you know. So I'll give the mic to Oliver. And I also want to say thank you to Vladimir, who's working at Schibsted, who's helping us a lot, and an Stockholm AI member.
Unfortunately, I have to admit that I'm a mathematician. Heard very bad things before. And you can see from the Beamer presentation that this will be a very technical talk. Yes, so I will talk about differentiable neural computers, DNCs, and they were introduced by Alex Graves and others at DeepMind in this article, in this paper. And it's a novel way of combining symbolic and numeric computations. So by symbolic computation, I mean algorithms operating on variables or data structures or mathematical expressions that are independent of the values of those things. Yeah. And the first iteration of this construction was called a neural Turing machine. And this is because it's very similar to the structure of a Turing machine, you will see later. And it's basically a neural network with a memory. And the whole thing lies in how the communication with this memory is done. And that's what I will mostly talk about. So to recap what a Turing machine is, it consists of this tape, this memory tape, that contains values and a read and write head that can read and modify these values, and a program with instructions that dictates what the head should do. And what you learn with the DNC is this part, the instructions. Or that's what you're supposed to learn. So the structure of the DNC is quite similar. You can see here's the controller thing, and if you would only have an LSTM, this is what you would have. And here is the memory part of the architecture. So you have an interface here between a controller and how you read and write to the memory. And then you have some additional functionality like memory allocation, and you keep track of temporal connections. I will talk about this later. But how you do this is basically you construct a distribution over the memory. That's how you make it continuous. So when you write to the memory, you write to several locations, but using a weight. So yeah. So why is this interesting? One reason is because it's this type of models are state of the art for several problems, but it's also interesting because it introduces a way of adding external structures to neural networks to store data over long time scales and represent complex data structures. And it's also gives some sense of interpretability of the network. You can, in some cases, reconstruct kind of what it does. It's a step in this direction, at least, and that's something that's a lot of research in currently. And it's also, there are some parallels with how the brain works as well. So that I'll show you an image of the brain. So this is how a picture of how the brain represents objects. And it's not like one specific region represents a car. Each color here is an object class. So, and you can see that the same color is all over the place. So it uses, and they overlap, and it's a mess. But the thing is that it uses different parts of the brain to combine it to represent one object. So it makes sense to have some distribution over the memory, because you get you get more power of expression with this way, in this way. Okay, so now we have the basic idea, kind of. Are there any questions at this point? Yeah.
Can you just give some examples of what it's good at?
It's good at copying things. So if you give it a sequence and ask it to copy this sequence n number of times, it can kind of do that. An LSTM could not do that for large n. It can solve, yeah.
What's the difference between the previous iteration, the neural Turing machine, and the differential neural?
How it interacts with the memory. So it uses different mechanisms for this.
What were the main problem with the neural Turing machine that is now solved here?
The temporal links and also how the memory is used. In the DNC, you keep track of what memory has been written to, and you can overwrite this memory in a way so you don't write over important information, and you still can keep track of temporal links in a good way. In the neural Turing machine, you just wrote to memory and you didn't keep track of what was important, and temporal links were just you had a sequential way to iterate over the memory that was not very good.
So this means that the memory allocation is also differentiable?
Well, except for one small detail. Yeah.
One more question. So some people say that DNCs is especially useful for graph problems,
Yeah.
question answering or finding shortest paths and stuff like that.
Yes.
Would you say that that is the main use case, or are there other use cases that are especially useful for DNC?
Those are the problems that are addressed in the paper and the problems I will talk about. Yeah, I will give some speculation at the end.
Has it been applied to this kind of bounding tasks where they
Yes,
correct it? And do they outperform?
they're not best currently. Oh well, I mean a version of DNC is currently state of the art. It's called entity networks. Okay, let's continue with the details. Okay, so you saw, maybe you remember from the architecture that we have kind of three different parts. The main part is the controller, and then you have two parts. You have the writing to the memory, and then you have the reading to the memory. And they use different mechanisms to interact with the memory that we will go through. So first the controller, and the controller is can be any type of network. In this case, it's a deep LSTM network. For the neural Turing machine, they also experimented with a feed-forward network. It works well for some tasks, and it's faster to train, but LSTM is better. So the DNC gets some input xt at each time step, and it should output some y of t. And the controller gets the following input. So it's x of t, and it appends what it has read in the previous iteration. So you have a number of reading heads that at each iteration read something from the memory. And this is appended as an input to the controller for the next time step. So you can view the controller as this network M, that's a function of all the input it has seen so far, and some parameter values theta, and it outputs a vector ny, which will be used for the output, and an epsilon, which is called the interface vector and manages the communication with the memory. And the output is... So the thing is that you want what you read in the current iteration to be included in the output. But you can include it here because of a circular dependency. So you add it afterwards with some linear map. Okay, so for the controller we have the following. These are the equations for an LSTM for each layer. Yeah, most of you have probably seen these already, but I can go through them if we have time later. Maybe I should. But the point is that you have these the hidden vectors that you get in each layer, and the output and the interface vector will be some linear map based on these. So ny will look like this, and the interface vector is some linear map from based on the hidden vectors. Okay. Do you have any questions about the controller? Which one? What? Back which way? Oh, yeah. I will. That's this slide. This is what the interface vector represents. Well, what information is contained in the interface vector. And as you can see, it encodes a lot of information. So the first K here are read keys. So these are used in the reading part. And these beta R's are read strengths. So yeah, how you scale the distribution of the reading weights. KW and beta W are the same for the writing part. E here is what you should erase from the memory. V is what you should write to the memory. These Fs are used in memory allocation. These GA, GW are used to scale between the allocation weights and the content-based weights. And these pi here control how you should read from the memory. And we'll go through all of this. So the first part is writing to memory. And it's done like this, that you choose what you want to erase, and then you add what you want to write. And this is controlled by a weighting vector. So this is your distribution of the memory for the writing part. And it's defined as follows. So it's you weight between. So GA controls if your distribution should be chosen based on the allocation part, or if it should be based on attention. The content. If the content is important, or if you just want to write something new. So if you want to overwrite something that you want to replace, or if you want to write something new. And this GW, it controls if you want to write at all. If it's 1, then you will write something. If it's less than 1, you will have some probability of not writing anything. So you can see that there are two attention mechanisms at play here, content-based and allocation-based. No, it comes into the reading part. So for content-based addressing, what you do is you define the distribution based on how similar the entries are to some vector you want it to be similar to. And in this case, these are the writing key that comes from the interface vector. So you give a writing key, a writing strength, pass in the memory, and then you produce this distribution over the memory. And yeah, exactly. And this d here is a metric, which in the paper is chosen to be the cosine distance. And the beta here scales. It flattens the distribution if it's chosen to be low. So. Any questions on the content-based addressing? Then we move to the allocation part. So how do you control memory allocation? Well, what you do is you define a usage vector. So this tells you at each memory position how important that is. So you take what was important before, then you add what you wrote in the previous iteration. So this is the addition rule for probabilities. And you multiply it by some retention vector that encodes what you read in the previous iteration. So it's defined as this. And you might have noticed these FIs, they were in the interface vector. And what they determine is how important what you read before is now. So if what you read before is important, they will be 0. And that position will be as important now as before. Otherwise, you will erase it. So the usage vector says how important a location is. But now you need to encode this in some, you encode this in this allocation vector now, where you sort, you need to have a you have this free list, which is this phi, which keep track of the indices of the usage vector that are least important, that you can write over. And you sort the indices of the usage vector to so that the first index is the least used, the one you can use the most. And then you define the allocation vector as this. And this will be this will have the highest value at phi 1, and then it will be decreasing. So you will get a distribution of how important the memory is.
I've heard some people trying to describe the intuition behind this.
Yeah.
Some people basically says the intuition is if you read it recently, it can be overwritten.
Yeah.
That to me sounds a bit weird.
Yeah. It's controlled by the free.
Yeah, but
Yes.
why is it just because you recently read something? Does that mean you should erase it?
Yeah, I know.
I think that's a bit weird. How about if you read it, it means you have the information somewhere else where you read it.
Mm,
Yeah, that could be it. Maybe. To me, it should be more of a least used kind of thing. If you read it many times, it's more important. But it could be, as you say. But I still think this intuition is not super intuitive.
yeah, I agree. Exactly. Because you feed it into the LSTM, so it should be captured.
This memory is supposed to be external. You should not rely on the LSTM to carry memory. It's supposed to be external memory. You should keep the most important memory.
But wasn't this F an output from the LSTM that says
Yeah.
how, like, should it erase it or not? And then
Exactly.
it's not related to how recent it is,
Yeah,
but
but still,
variable.
yeah. But at least the temporal aspects that gets read from it, to me, that intuition that I've been explained at least says basically, if you recently read it, it can be erased. And that to me, if it's true, I'm not sure if it's true, but if that's true, that's a weird.
I think in humans, when we remember something, we always change the memory. So it could be the case that you're arguing that when you remember something, we always store it in a new place. So then you should erase the last one. And for humans, it works so sometimes.
Maybe.
That's an argument.
Yeah.
I have a question about this sorted tree list. How is it differentiable with sorted?
Yeah. It's not.
So I have a question. I don't understand the math so well, but with the memory, is the system, does it keep track of how important each memory is? In a way?
Yeah.
Does it weigh it in some way? Or? So instead of like, we just remove them when they're being close, is it a way for them, a mapping of how important memories are? Because that seems to be key if you want to make it like a human, I guess.
Okay, so if I understood correctly, this is not based on any temporal aspects. And the allocation vector, it says how important a memory cell is.
Okay. Alright, okay.
Yeah.
Okay, cool.
Quick question. Have you ever tested these networks for the same input, like zero input? How long time do they hold the memory? Do they converge to some? Do they decay somehow the contents of the memory? And some parts remain stable, and some parts just does the state is continuously updated?
Yeah. I can't answer that. Yeah, good question.
Okay, if you have this continuity here, how is that resolved?
You ignore it, and it works anyway. Yeah.
But answer to your question about stability, like there is one parameter that is like, should it read something or not?
Yeah. Yes.
And if that is, or write something or not. And if that also goes to zero, then it should remain stable. At least in theory.
But I haven't read any paper where they actually have tested this thing out to see that, because all the states they propagate from time to time, right? And at infinitum, if they will be stable at some moment and have some fixed memories that will never be erased. That was a question I had.
Let's keep going because there's only time.
Okay, so now we're finished with the writing part. So we have the allocation weighting and the content-based weighting, which was here. So this is how we choose the weighting of how to write to the memory. And now we come to the reading part. And so how you read from memory is just like this. You take the memory, and then you have some weighted linear combination of the rows, and that gives you what you read, basically. So what we need to compute are these WRIT, so the reading weights. And this is controlled using 3 mechanisms. It's basically 2, a content-based weighting and a temporal linkage. And these pi here control which of these 3, the content-based, the forward temporal weighting, backward temporal weighting, we should rely on. So forward temporal weighting means that you should read the memory locations in the order in which they were written, and the backward temporal weighting is that you should read them in the reverse order. So you keep track of temporal information with a linkage matrix, where the ijth location gives you the probability of row I being written to after row j. So you can see it here. This is this gives you the probability. Here you remove if row I have been written to in the current iteration, then you remove the old information. Right. So if row I and row j have been written to, then you need to update this information, so you remove it from the old linkage matrix, and you update it with this new information, the weight for row I times the previous p, where p represents the degree to which row j in this case was the last one written to. And it's defined like this. So for each time t, this gives you the probability that you did not write anything. So 1 minus the sum of the weights. And so if you didn't write anything, then look at the previous p. Otherwise, you look at the weights for the writing distribution, because this gives you the probability of writing at row j. And then you compute the forward weights by just multiplying the linkage matrix with what you wrote in the previous iteration, and the other way for the backwards temporal weights. Do you have any questions for this?
So let's say that the probability comes true of writing somewhere, so it's actually replacing the value, the new value, or does it use the previous value?
In the matrix, or?
Yes, like does it erase this memory and put in a new one, or does it just change the
Do you mean the memory now, or the linkage matrix?
The memory.
So you have this erase vector that tells you what to erase from this slot, and then you add what you want to write. So what was previously there is just modified by this process.
Yes.
Quick question also. What would you say the intuition using temporal links is? Do you agree with saying something like, if you think of a question answering system or some kind of graph problem, that this basically can represent saying if you asked this question before, then it's more probable that a certain question will arise afterwards. And this is really what's being represented by this link.
Well, that depends on how it's stored in the memory, because, or what you represent in the memory, because if you represent a question as a slot in the memory, then yeah, this would give you that information, I guess, because it's, and if you heard, so if you would rely on the forward temporal weights, this would then give you a probability of reading the next question, so I guess. Okay, so now I at least have defined everything that we need for reading from the memory. And yeah, what we need are these three things. The content-based weighting is the same as for the writing part. And these pi give you a weight on which of these three mechanisms we should rely on. So it's like a mixture of Gaussians. Yeah, so do you have any questions about the mechanisms? Yeah.
I think I have a really stupid question. Go back. Size of this
It's usually 64 bits.
Oh, sorry. No.
Or 64. No, not 64 bits. Oh, which W do you mean?
Right. Maybe it's not on this.
The weight vector or the
Actually, I want to know about the read.
the read? Yeah, that's the number of rows in the matrix. And the number of rows in the experiments is usually 256.
And with the matrix, you mean the memory?
Memory, yes. Yep, the memory matrix.
I think that needs to be hypertuned in a good way.
Yes, yes. That's true. Okay, so one experiment I will talk about is the shortest path experiment. So there are three different kinds of graph tasks that are presented in the paper, and the I think the hardest one is the shortest path. So what you do in this case is you give the DNC information like this. So you give it a tuple of names. These are paths in a graph. What you do to train the network is to generate random graphs, and then where you name the nodes, and you ask it to find the shortest path between two nodes in the graph. And you do this by asking it questions like this. And it should give outputs like this, where it gives you a path to go. Yeah.
How long can this path be? If we have 1,000 or 10,000 nodes,
Yeah.
does it really find the shortest path in 10,000 nodes?
Well,
Same as
it maybe it could if you had a big enough memory, because it's very dependent on the memory, I think. How many rows you have to be able to represent the information.
some relation, how much memory versus how big the graph can be.
I think you have to tune that in hyperparameter search. Yeah, I was planning on showing you a video, but maybe you can watch that yourself afterwards.
The DNC is trained supervised, right, with
Yes.
models. So,
For this task, it's
for example, like shortest path. Do they have to know the shortest path?
yes.
Some examples.
Yeah, just to add to that, like, yeah, they know the shortest path, but for a random graph, so you can provide like a new graph for the short paths. Yeah. So that's the generalization.
I mean, just creating training data requires having a way of actually finding the shortest path.
Sure, but you can also train it with reinforcement learning. Yeah, I think I'll just jump. So another problem is this puzzle called MiniSmarter Lu. Yeah, so the Lu is a kind of a language to test reasoning, and this is a mini version of this, where you are given goals like this that says that 6 should be below 2, stuff like this, and then you feed that to the network, and it should and you represent this state somehow, and it should move until all the goals are satisfied. There's a video showing this as well, so it's connected to the paper, so you can watch this. So then I just wanted to say something about similar architectures. So since the neural Turing machine was introduced, a number of other architectures have been introduced as well. And there's also a description of an implementation of a DNC that's quite interesting to read. They discuss problems with instability and gradient spikes during training. Yeah, and which part? Well, in some sense, I guess.
What is the reference here? I want to note it down.
Oh yeah, there's a reference list in the end, but I'll upload the slides, I guess, somewhere. Yeah, so just a comparison on this bubble test that you mentioned. Yeah, this is from the entity networks paper. So yeah, you can of course see that entity networks are the best one. And this data set, it's a natural language processing problem where you should reason from some text input that you're given. It's a question answering problem. And these entity networks and dynamic memory networks, they are specifically designed for these types of problems. So it makes sense that they are better than the DNC. But the DNC is quite general architecture. Yeah, some speculation. So yeah, I mean, it could potentially be used for building models for intuitive physics, since you can use it for image inputs and stuff like this. And there's some research in that area, I think. And you can potentially use it to discover new and better algorithms, maybe for automated theorem proving, things like this. and also finding approximation algorithms or heuristics for NP-hard problems like Euclidean TSP. There's at least one paper addressing this. And also, yeah, you can try all sorts of memory distributions. Yeah, that's it. Thank you. Yeah.
Yeah, got pretty much the same question as Carl. Like, are there examples where the DNCs have solved the unsolved problems?
Well, so there is at least one paper here. They don't use a DNC, but they use some. It's like they learn a meta heuristics for a meta heuristic on TSP to get better performance than some other types of heuristics. It's not it's not better than this, but it's for larger instances of the problem. It's pretty good, but yes. Yes. Oh, sorry, maybe I misunderstood you. Did you mean if it was state of the art on any data sets? Or? No.
You have to generate targets for training, and if you can't solve TSP, or if you could, why would you even do it? I mean, how do you generate training data?
Rather like, are there situations where DNCs are better than any other?
Oh, but
like for example, shortest path is already solved, right?
wow, that's a bit of a stretch. Well, I mean, so for the TSP problem, you can use reinforcement learning to potentially learn a better, either a meta heuristic or a new heuristic. And then you, given enough time and hyperparameter tuning, you could maybe get something useful.
I think it's important to just recognize that if you just want to do graph search and just have nodes and edges, then this is not the type of solution you would use. This is when you have a lot of more context related to like what type of text it is or question answering that is represented in some higher dimensional space. If you just have like one-dimensional graph structures, you would, I would say, not use this. Would you agree?
I'm not sure. I mean, I like the idea of capturing graph structures in this way, because if the network can understand the graph structure and be able to reason about it, then maybe you can find some good algorithm for like discovering communities in a big graph or something like this. I mean, it's there's like discovering communities. I think it's a hard problem. So, like generating graphs similar to social networks, that's also a very hard problem. So I think there's potential in that area. Yes. So the image would be basically you just put a CNN before you run it to the controller. So yeah, that's one strategy.
Yes, my question is the source code available, and is it like
yes.
How is it have you played around with it? How is it just to do stuff with it, or is it kind of too abstract to kind of make things useful? I mean, so I'm asking because I have some courses in deep learning and looking for like fun things to play around with.
Hmm.
I'm asking if this would be something that would be cool to play around with.
Yeah, sure. I mean, there is source code available by DeepMind, and I mean, yeah, it's relatively easy. Maybe I don't know. It depends on what you want to do. I mean, it comes with some examples that are easy to get started with.
Right, but once you get out of the example, it's really like you hit a brick. It's hard.
I don't really know.
Okay. But there's source code from DeepMind.
Yes.
Cool. Thanks.
So some people say that this is especially useful also for one-shot learning, and I think that's a very important area.
Sure.
Would you agree, or can you think of why it would be especially useful for that?
Well, from what I understand, the reason why it could be useful in this area is because for one-shot learning, I mean, it's not one-shot learning. It's like based on a lot of previous information, and using the memory, you can try to capture this previous information to learn new tasks using what you know. So, I mean, that's my personal opinion. I don't know.
Any more questions? Okay. So I think now we're going to relax and eat something, maybe drink something. Nokiana, for example. Is anyone here not joining? I was assuming that, but yeah, that's very nice. Moreover, thank you guys for two very awesome presentations and awesome questions also. I really like all the questions and Lars also told me that there is a next session upcoming for the 2nd of November, right? And don't invite too many people because it's getting Thank you guys.
Grym presentation. Tack. Jag förstod inte all matten, men det verkar ju bara